Okay, I thought it was 25. You changed it. Oh, well. All right, over to you then.
Okay, thank you. So, yeah, let me take this opportunity to say thank you for your hospitality. And yes, I really enjoyed these 3 weeks. Yes, so today I want to present work with Florian Maire. He is a lecturer at University of Montreal, Canada, and NIL. And yes, so I think I can definitely skip a few of the introductory slides. The idea is that we want to model this type of object, a network, and as we have seen yesterday, there's quite a lot going on here. There's a lot of complexity, heterogeneity we want to capture with our model. So the models I'll talk about are called latent position models, and this name is used for the Waxman random graphs in the social sciences. Okay, in 2002, these models have been used for the analysis of social networks, and they've kind of kept that name since. So the idea is, as you have seen in Kathleen's talk, these models assume that the nodes are localized. They have a latent position in a social space, and the probability of observing a certain edge depends on the distance between these two nodes. So the idea is that we need all these distances between nodes so that we can evaluate all the probabilities of edges appearing. Now, in this paper I mentioned from 2002, they used this particular function for the edge probability. Okay, so the logit of Pij depends on an intercept beta, and it depends on the distance. Now, as a consequence here, if the distance increases, then the edge becomes less likely, and vice versa. Now, this is a simulated data set, a simulated latent position model, and there's quite a strong message in this picture, because essentially, if you just look at the graph we had before, yeah, so this is much more, this is, of course, very complex object, but here, in some sense, the heterogeneity in the graph can be explained exactly by the latent positions. Okay, so this is on purpose. I generated this data with a strong effect on the latent distances, meaning that the latent distance, the latent position of a node essentially determines all of the edges. So as you can see, there's no long edges, right? And we're capturing all of the heterogeneity in this graph with the latent distances. So yes, why we want to use a latent position model? Well, the main message is that they're very easy to interpret models. Okay, the interpretation may be quite straightforward. If you have a node in the center of this latent social space, then we just interpret that saying that this node has a central role in this community, right? If you have a node in the outskirts, then the role played by that node is not as important. Another idea that I like to mention is that essentially we're switching from a square matrix, the adjacency matrix, which is of size n times n, into a new matrix which is much smaller. Okay, n times n potentially is huge. We're talking about, for example, if we analyze a network of 1 million nodes, this is a type of data set that we can't possibly represent in any way. Well, the latent position model will allow us to reduce that dimensionality into a matrix which is much smaller. And well, if we infer these latent positions, then using that we can extract some summaries from the latent positions, which are of course quite interesting. You can look at the empirical variance, for example, of this point process. Now, I'll also make a connection here to another paper I worked on at the very beginning of my PhD. And in this paper, essentially, we looked at the properties that latent position model exhibit. And we found out that these models are actually very useful for social networks, for okay, applications to social sciences, because in social sciences, all of these properties are quite distinctive, okay, so they often appear in social networks. And we essentially showed that latent position models are able to represent all these. Okay, so let's get to the actual problem we want to solve. If we just write down the likelihood, as we have seen yesterday, this will just be a product of many Bernoulli random variables, but differently from yesterday, these Pij's will be different for any pair of nodes. Okay, so this value will be different for every I and j. And this is quite complicated, okay, because we have essentially a product of O of n squared terms, and this quadratic computational cost is impractical for us, because yes, as we increase the number of nodes, we will not scale well. So the idea is that observed social networks are actually relatively easy to obtain, and very often we get networks with several thousands to billions of nodes. So really, there's a huge gap here in terms of computational feasibility. Our goal then eventually is to actually define something that can scale better, at least, than what we have. Well, I'll give a brief description of what we have, okay, of the available method to infer these models. And it's very, I would say, it's very straightforward Bayesian setup. You just specify a prior on the intercept. This is just a Gaussian, and on each node in each dimension, you also specify a Gaussian prior. Then you define the posterior distribution of this model, which is, again, you have the parameters are independent a priori, so this is also quite straightforward, and you want to sample from it using Metropolis within Gibbs. So in every step, you update one of the parameters. Now, when you update beta, you need the full likelihood. Okay, so that's already an n squared cost you have to evaluate. And when you update the latent position, usually you want to update the two coordinates in block, and still that's the cost of O of n, and you repeat that n times. Yes, so if, in case you're wondering, there's a problem here, and the likelihood depends on the latent positions only through the distances. So if you start translating the nodes, or if you rotate the nodes, the latent positions, or if you reflect them, then you're not going to change the likelihood value. Okay, so if we sample from the posterior distribution, we will not actually be able to interpret the parameters afterwards. Well, this has been addressed in the past, and we have a pretty good solution for this. So I will not spend much time discussing this. We'll just use the best tool that we have to make this posterior sample identifiable eventually. Okay, and it's simply based on Procrastis transformation. So what we'll do is re-rotate the latent positions to match a reference configuration. Okay, in this paper, I'll essentially introduce an approach that we can use to speed up inference. Okay, we'll start from the basic MCMC, okay, Metropolis within Gibbs, and we want to find a noisy version of that algorithm that can be much faster. What we want to use is this type of grid partition. Okay. So we're looking at the latent space in 2 dimensions, and we just want to define a grid on this latent space made of boxes of equal size and sides aligned to the axis. And the situation we have is that whatever the latent position of a node, there is one and one only box that will contain it. So we're essentially partitioning both the latent space, and we imply a partition on the nodes. Now, why is this advantageous? Well, because if I know that a node is inside a certain box, I can use the center of that box as a proxy for the latent position. Okay, and a similar idea has actually appeared. I got this idea of the grid partition from a paper from Matthew Ruffin and some other people in Adelaide, but they use this approach for simulation. So I thought, well, the next step is, to try to use this for inference, and that's our proposal essentially. Well, going back to this mechanism, well, if I need the distance between I and j, and I know that j is in box gh, then in practice what I want to do is just to approximate that distance with zi minus the center of box gh. Okay, this is just to fix the notation. And I will also introduce the approximate. I will induce, again, an approximation on the edge probabilities, and this P tilde ij will denote that. So again, this will imply, in turn, an approximation on the likelihood. Okay, so we had our likelihood before; it was a product of O of n squared terms. Now we have a new likelihood, a noisy version of that likelihood, where we substitute all the edge probabilities with the approximate ones. Now, since we're using the same center of the box to approximate many different distances, then we're actually grouping up all these PIJs into groups, right? And in each group, the number of same values that you have is given by this eta igh, which denotes the number of edges that go from I to box gh. Okay, so we're essentially clustering in some way the nodes so that we don't have to reevaluate too many times the distance. Now, in practice, what we want to do is to do the metropolis within Gibbs using the noisy likelihood. Okay, so we want to essentially save time in computing when we compute the likelihood, and I will refer to this new algorithm with NoisyLPM. Now, the properties of this algorithm would be that if the boxes become smaller, then the error decreases, and yes, also the computational cost will increase, okay? Because this likelihood function will essentially, the computational cost of this evaluation will be O of n times the number of boxes. Okay, so if we increase the number of boxes, the boxes become smaller. It's better approximation, but higher cost, or we have vice versa, right? So this parameter b, which is the side length of the boxes, will essentially give us a trade-off between speed and accuracy. Now, the main point we want to address is the error, right? Can we quantify in some way the error that we obtain with this kernel, with this metropolis within Gibbs? And in the current situation, what we're doing is, of course, we sample with this algorithm, and this algorithm will allow an invariant distribution, which I call pi tilde. And this pi tilde is not the one we're interested in. We need to, in some way, quantify the distance. In this case, it's a total variation distance between the correct pi and the approximate pi. But yes, in practice, this is quite difficult to study. So we kind of decided to work with something else. We decided to study the incremental errors. Okay, so instead of looking at the asymptotic distribution of the two chains, we look at the error that we accumulate as we iterate the kernels. Okay, so yes, there is actually a strand of literature in MCMC that deals with approximate kernels, and also Niall and the next talk will talk about this, and it's called NoisyMCMC, and yes, it essentially allows you to study how the incremental error can be bounded if you use an approximate kernel instead. Now, before I give the main result, I need to introduce a few assumptions. And yes, the first one is definitely a very strong one. We're assuming that the parameter space is bounded. this means that the intercept is in some interval, and all the latent positions are in a sort of box. And it is quite a strong assumption, because none of the latent position models actually assume this. But our argument is that if you actually let the parameters be unbounded, okay, with very large parameter values, you get networks that don't necessarily make sense. So they're degenerate, meaning either they are full or empty. So yes, that's essentially our argument. It's not satisfied by the models that are used, but it doesn't really occur. The opposite of this assumption is not really happening anyway. The second assumption is quite okay. We are just assuming that the edge probability function is regular, and in particular, it must satisfy Lipschitz continuity with respect to the distance, and most of the latent position models satisfy this property, so this is no problem. Okay, well, this is the main result. There are several intermediate results that allow us to get to this point, and I will give the link to the paper at the end. But yes, this is a summary of what we prove, right? Well, we call P the exact kernel, and we call P tilde the noisy kernel. And we're assuming also that P is uniformly ergodic. Now that is okay to assume. We actually prove that for the latent position model this is the case, exactly because we assume that the parameters are bounded. And then for any starting point, essentially we can bound the incremental error after t iterations with k, lambda, and c are constants. This tau part goes to 0 as this whole thing essentially is a constant test that does not depend on B, and the dependence on B, on the grid structure, is just here in curly brackets. This function psi is right here, and it actually involves several constants which I'm not writing explicitly, but yes, these constants do not depend on B. So essentially, as the main point here is that as B goes to 0, then this thing in curly brackets also goes to 0. So we're saying that we can arbitrarily regulate the bound on the iterated kernel, on the error on the iterated kernel, as B goes to 0. Well, the main result we rely on is from Mitrofanov in 2005, where it shows essentially a general theorem on the error bound for noisy MCMC, and yes, so this I have said already. One comment that I need to make is that actually we may be interested in understanding what happens if the number of nodes increases, but yes, this theorem is not good in that case. We are assuming that the number of nodes is fixed. If you let the number of nodes increase, then the bound will also, the bound value will also increase. So the theorem is, you must assume also that the number of nodes is fixed, otherwise it's not useful. Okay. We performed some simulations to kind of check what's going on with this error, and we have generated two latent position models with a fairly large number of nodes, 200 and 600, and for both data sets I will use the standard procedure, which I call ground truth, and the noisy procedure. And in the noisy procedure, we arbitrarily fix the grid. And I will choose 64 boxes and 256 boxes. So it means on each axis we have respectively 8 or 16 intervals. After sampling with both methods, we just use the Procrastis transformation to solve that identifiability problem. Now, what we want to do is that we just look at these two samples, okay? okay? And we want to see how close we are with the noisy procedure to the non-noisy procedure. Well, this is the result in terms of computing time. So for the best result is essentially for the larger network. If we use few boxes, okay, 64 boxes, then we get a reduction of factor of 3, so about 1/3 of the time. Yes, so actually in the next application, this will be a much larger, much better improvement. Well, in terms of the posterior density, this is the posterior density for the first node, and the first node I arbitrarily located this in the origin of the space, and this is the actual posterior sample, posterior density we get from that node. The black line is the ground truth, so the standard procedure, and essentially with the other two noisy variants, we pretty much get exactly the same shape. Now it's probably a bit difficult to read, but yes, there is very, very little difference between the densities in the two approaches. Here we're looking only at the posterior means of the latent positions. We're only looking at the large data sets, so we have 600 points, and the black points are the true positions, sorry, not the true position, the ground truth positions, and the colored ones, or either green in this case or purple here, are the ones we estimate with the noisy procedure. So as you can see, if we use 8 intervals, so meaning 64 boxes, then there is some error, some bias in the posterior mean. But yes, with more boxes, essentially, it's, you cannot really recognize the difference. We also looked at the edge probabilities, because we can reconstruct the network if we want. So we want to look at the estimated edge probabilities for every pair of nodes. And these are essentially, again, a comparison of the true ones with respect to the noisy ones. Sorry, it's not the true ones, it's ground truth ones with respect to the noisy ones. And there's pretty much no clear bias, maybe on the larger values, so the more likely edges are a bit, the probability is a bit overestimated. But yes, in general, I mean, this is very probably encouraging results, but the problem may be that as n increases, also we have a problem of an increased bias or error, right? Because from this plot to this plot, there is definitely some inflation of the error. Okay, I also have a real data application. Here we're looking at quite a large network. We have almost 20,000 nodes, and each node is a researcher. And the edges between researchers essentially mean that they have co-authored at least once a paper appeared on the Astrophysics archive. The network is very sparse. We have only 21 as the average degree. And here we could only use the noisy algorithm because, well, the standard procedure took quite a lot to run each iteration, so we only ran that for just a few iterations. And we get an extreme improvement with the noisy procedure here. And this is how it looks like. So we're only looking at the latent space. These are only the estimated posterior means of the latent positions of each of the nodes. So we have essentially 20,000 nodes. Now the idea is that, of course, there's not a lot to say about the positions themselves, but in terms of the macro structure of this network, we definitely managed to reconstruct it, because we will have essentially communities of nodes like this one here that are more connected between themselves than with respect of the rest of the network. And there is this curious effect of the nodes essentially concentrating in close to the center of the box, but this should not be surprising because, well, we are using the center of the box as a proxy, right, for the latent positions. So if we replace the true position with the proxy, then automatically the nodes will kind of converge towards the center. So in some sense, we could say that overall the structure is well recovered, but if you look inside each box, then not necessarily we have estimated well the latent position inside each box. Okay, so, well, in practice, the method clusters the parameters of the model, and by doing that, we were able to reduce dramatically the computing time. And one point to make is that this is actually not necessarily a method for networks. You can use the same approach for any type of latent variable model, and you can study the error in a NoisyLPM framework with many other types of models. And yes, that's of course, in our network context, it is quite useful because, well, we can, for this particular model, achieve quite a substantial reduction. But yes, one drawback is definitely that we were not able to include, for example, covariates, because in that way you will have inside the same box nodes with different covariates value, and that may simply imply that the nodes are not homogeneous inside the box, so you cannot cluster them together. In other words, you would need more dimensions in the grid, which is, again, not computationally practical. Okay, so that's the main reference. Actually, it's probably it will be updated relatively soon. We have done some more work on this, and this version is relatively old now, and hopefully it will be the new version will be up very soon.
So, some questions.
Everybody's tired.
By latent position, you mean you reduce the dimension and
you can think
PCA or something.
Well, no, we don't use PCA, but it is in the same flow, right? It's the same idea. Like we're moving from a matrix which is n times n into a much smaller matrix. So the first matrix is binary. So it is. I mean, it is one way to reduce the dimension of the data. Now it is in some.
It is actually binary data or count data.
No, binary. In this case, it's binary. Yes.
And reduce the dimension to 2
n times
make the grades, yeah.
n times 2. Yes. Yes. Thank you. Yes.
It's very similar.
Yes.